Hello everyone, I'm not here to talk about the bus and transport. What I'm actually here to talk about is the work that I did for my master's project. So I'm currently a PhD student at Christoph Federer, Mike Island and Kenny King. But this is the work I did here with Mike Island and Christoph Federer. So tiny grains shining bright in the gaps of Herbig, so I'm going to tell you why I'm looking at them, how I looked at them, and tell you what we found. So protoplanetary discs are a stage of evolution, everything forming and big planets at the end. So at the first stage, you have the cloud is collapsing. So they're really heavily embedded, and you can't really see this yet. So that's still a protostar. Here you've got a heavily embedded disk. So these class 1 objects are things like H-Power, and you can see a disk, but it's really heavily embedded if you try to look at it in different wavelengths. The objects I study are these class 2 disks, so they definitely have a disk. And then a further stage of evolution is 3 disks. So the disks you've already seen this picture in Dana's talk. So there's different stages or different shapes and forms that they can have. So they can get all the way down to the star, up to the sulfidation radius, or you can have a cleared inner region, or you can have a partially cleared inner region where you still have some material here. So the ones I study are these two. So yes, there's other kinds of features that you can see in discs. So here we have HL tau, which has rings, and I-226, which has spiral arms. There's been a good introduction to those kinds of features there. So one of the objects I studied is known to have asymmetries in the outer region of the disk. So at about 60 AU, there's a spatial separation of the millimeter-sized dust grains and the micron-sized dust grains, creating this big asymmetry here. There's also a concentration of centimeter-sized dust grains here. So it's thought that this disk has a dust trap, which means dust is close to the ground, but it's getting stuck due to pressure and density gradients throughout the disk. It causes a trap. So Oph IRS 48 is an A9 star, so it's going to be AE. And the other object I studied was HT169142, which is thought to have a baby planet in the disk. So the reason that we look in these disks for planets is so that we can get a better understanding of planet formation. So if we catch a planet while it's forming, it gives us a better idea of how or where this happens. So these are both in the Oph IRS filter. More about that in a bit. And yeah, so the potential planet is here. So the observations I used were taken with the L prime filter on the NERC2 NERC2 camera on the Keck 2 telescope. So we don't use aperture masking or coronagraphy, so they're full pupil images. Signal to noise ratio is very high, and PSFs are quite stable. The reason we look in this wavelength is so that we can see warm dust, so particularly in the inner regions. So rather than some of these other observations out here where you're imaging stuff at 60 AU, large dust grains quite far away, we're looking at the inner regions within about 20 or 30 so here some of my two objects. So this is Oph IRS 48 and this is HT169142. And what we've done here is deconvolved them. And that's what's shown here using the Richardson-Lucy V convolution. So what that basically means is when, I think Alex showed this in his talk yesterday. So basically you have a, what is there, and then it comes through the telescope and gets turned into something that comes out of the telescope, which has been convolved with PSF, a point spread function. So here we try and deconvolve it and work out what we actually think actually is up. That's one way of looking at it. But another way that we look at it is to take a forward modelling approach. So we make a model of the disk that we think we have, the disk structure. We use using random C3D. And we convolve this with a point spread function. Make it the same as what comes out of the top squares. Then we compare that to our actual data. And we explore the parameter space used to make these models with MC. So there's quite a few parameters, so I'm going to step through them. So we have, so this is our disk. We have this is one parameter, the very inner radius of the disk. There's a wall here, the second wall here, this red line, and there's also the inclination, so and the position angle, so there. So here you can see a density radius plot. So here's the radii here on the graph, sorry. And here we can change the amount of dust at each wall and the total amount of dust. So all of my models use all 8 of these parameters. But this is the base for our symmetric model. Next, we can move the star in the disk, so it doesn't move far, but just slightly offsetting it can create an asymmetric appearance in the disk. So that's our asymmetric models. And then our final layer of complexity is adding a planet of point source into the disk, which we can change the brightness and position of. Oh, no. Okay. Press the button planet. So here are some of my results. We found that to model the disks that we wanted to model at the wavelengths we're trying to look at, silicate dust of 0.1 micron and carbon dust of 0.1 micron weren't going to be bright enough to fit all the features they needed to be able to fit. However, small carbon dust that includes polycyclic aromatic hydrocarbon is. That's the pink line up here. So here's how that corresponds to the brightness. So this is the silicate dust. So these are all the same model, just with different dust types. I know they don't look the same, but that's what happens with dust. So here's the carbon. You can see one of the outer rings, and the inner disk is bright. But you need to be able to see this other ring out here as well, which is why our carbon and 5 nanometer dust works really well. So that's why the grains are tiny. 5 nanometers. So here are some SEDs from my 2 dust. So if you're still looking at spectral energy distributions, you'll be like, what is that? It's because there's a lot of extinction towards this star. It's very highly red. That's why the range is accurate. There's a lot less reddening towards the species once it's happened. So here's the symmetric, asymmetric planet models, involved, then the residual ratio, and that's what the dust looks like. So in IRS 48, we detect a planet-like asymmetry with walls at 13 and 30 AU. In HD 169142, it's the same layout. We find symmetric rings at 17, 7 and 15 AU. However, and we do find an asymmetry that is consistent with the position of the planet previous observations. So you might be like, why is the dust staying there? So to survive and not be blown away or drift in, dust needs to be about 3.2 micron here in IRS 48, and not microns, sorry, nanometers, and 5.5 nanometers to survive here. So that's why this tiny dust survives quite well. So that is my summary. We reckon we possibly found things that are similar to planets in